Tyler, you can start.
Okay, thank you. All right, so yeah, today I'll be talking about vector databases. Just a little bit of background on myself. My name is Tyler Williams. Let's see, I've been working with relational databases for quite some time. Currently focused a lot with Azure and working in Synapse and Azure SQL and that sort of thing. I work for Redapt based out of the Seattle area. So just jumping right in, some of this may be somewhat review, especially for people who have attended these seminars in recent weeks. But just to get a foundation for everyone, so we're all on the same page, just wanted to go over what a vector is. So a vector simply is just an array of numbers. This first example here is a very simple example, just if you think about a coordinate plane, and just you know, the two dimensions. You have a simple vector that's 2, 3, and it goes to that point on the coordinate plane. And then you can actually have a lot more dimensions than just those two. Conceptually, it gets a lot harder for humans to be able to, really conceptualize in a space what that looks like, but machines can handle many, many more dimensions. And so you can see the example at the bottom of the screen there is a much more complex vector. So now, how do we use data to represent complex objects? Okay, I just have an example here, and just kind of going from my background with more tabular databases, the way we might represent these two images are, in a tabular database, we might have a blob column to store the image itself, and then some columns to describe the images. So the object, they're both image files. They're of cats. They have black and orange colors, things like that. So and when you have a discrete number of fields or dimensions to describe your data, you're kind of limited because we have the same values to describe these two images, but you can see that they're very, very different from one another. So yeah, if you really want to represent these in much more detailed ways, you can be very limited with having a fixed discrete set of fields or dimensions to be able to define these. So an alternative approach would be to use vectors to represent them. And so here, this allows you to use many, many more dimensions to define the data. So in this case, these two images. And while they do share some similarities across some of the dimensions, other dimensions will be quite different from one another. One thing about vectors, the way they're defined and stored, particularly in a lot more modern databases, and particularly the vector databases that we're talking about today, and like the large language models and things like that used for AI, is that the number of dimensions that you have is going to be really, really large. So as you can see here, they can get up to 500 or well over 1,000 dimensions. And so if we had to define each of those, it could be a little bit unwieldy to manage in a regular tabular type database. And so that's where vector embedding comes in. So the vector embedding is the way to convert your data into one of these vectors that can have thousands of different dimensions to define it. So rather than having to come up with a tag for each of the different dimensions, the embedding algorithm will automatically do that for you. So it can be thought of as sort of automatic feature engineering. And so it can really save time and definitely, of course, reduces the human intervention to define vectors for each of these data objects. So yeah, typically you'll just have your raw data. It can be passed into an embedding model to convert that data into a vector. And then that vector will be how it's defined within the vector space. The vector space, of course, similar to what I'd shown in an earlier slide, when you have just 2 dimensions, it's easy to visualize that in coordinate plane. But with thousands of dimensions, it's a little harder to visualize
Tyler,
conceptually. Yes.
Can I ask you a favor? Can you go to this link on Hugging Face, which is on your screen?
Yep.
Just to show people what it is.
Yeah, so there's a slide that shows this a little later on too, but yeah, Hugging Face here, it has a leaderboard where it ranks different embedding algorithms. And so you can see a lot of different metrics that it uses here, including the number of dimensions that are included in the embedding in the vector, and then the sequence length, the number of tokens that can be used. And you can see, it's fairly typical for 512 tokens, but this one in particular has, over 8,000 tokens. I'll get into that in a little bit here in the next slide. But yeah, so you can see though just this leaderboard where the different algorithms are ranked, and they get an overall score for ranking here. So yeah, so that's this link. There's also a link here if you just want to learn a little more.
Just a quick question. It doesn't include the OpenAI embeddings, right?
It does actually.
It does?
And yeah, so the OpenAI embedding is number 11 here. It's this one that has the really large number of tokens that it can accommodate.
Okay, thank you.
Yeah, you're welcome. Let's see. Yeah, so yeah, just wanted to call out this link here to good reference for more information about embeddings. And I'll talk about Pinecone a little bit here in a future slide as well. So yeah, once you have your embeddings and you have the vectors that define where these data representations are within a vector space, then you can start seeing some groupings, and common data will be grouped together in this vector space. So this visual just kind of portrays that. And here, this was a screenshot taken several days ago, so you can see, yeah, the OpenAI algorithm here. It was ranked 10 at that point, but it's 11 right now in the leaderboard. And then links to that leaderboard again. Some more information as well on YouTube for how you can deploy the number 1 model using Python. So just a couple things about that information in the leaderboard. So particularly in reference to the OpenAI embedding model. If we take a token is about 4 characters in the English language, and then a word is just over 1 token, kind of average. Breaking it out, we can see that 8,192 tokens that OpenAI can accommodate is roughly equivalent to about 12 single-space pages of text, and that's really a lot of content. So, it's debatable whether you really need something that can accommodate that much just in one embedding, because it should be easy enough to break out your data into smaller chunks for embedding. So it's one potential argument for looking at some of these other models as well that may not have may not be able to accommodate as large a chunk of data, but that has other benefits elsewhere. So next thing I wanted to talk about is, why even use a vector database with a language model? What's the benefit there? So the database is really what you can use to store and be able to query these embeddings that you've created. So in particular, there are a lot of different uses. But for instance, if you want to be able to use one of these large language models, but be able to interact with data that will return results that are only with your data. So, for your company, if you want to restrict the query results to just being, your own data within your own company, you can use a vector DB and it'll limit those results. Another benefit of the vector database is that it can provide for more contextual queries. So you can have more ongoing conversations, and it'll be able to retain that history. I know we had a presentation a couple weeks ago about the long-term memory for AI applications, and that's where a vector database would come into play. Another aspect of the vector DBs, similar to like a tabular database, is that you can index your data as well, which is definitely key to be able to quickly retrieve results on your query. Let's see, another thing to keep in mind is that the model itself is static. So for instance, ChatGPT-3, that was trained on data from, I believe it was 2021. And so if you want to be able to refresh your data without having to completely retrain the model, that's where vector databases can come in. And then I have links to a couple videos here, a good high-level video on how that works, and then another one that's a little goofy but still gives a good explanation of vector databases. And then you can see here just a diagram that just sort of shows visual of how things work and how the vector database kind of works along with the language model, and your UI really kind of brings all these different pieces together. So now with your database queries, to get results, a lot of times you'll use the similarity search here. So these are algorithms to be able to quickly find the data that most closely matches what it is that you're looking for in your query. So this is done using an approximate nearest neighbor search, and a couple of the different ways that this can be accomplished. There's a cosine similarity, Euclidean distance, dot product. You can kind of see here some representations here. Just Euclidean finding the distance between your two vectors, cosine finding more the angle between the two vectors. So just different approaches to that. So one thing to keep in mind with these similarity searches is that the results will just be approximate. So speed really is the key result that we're looking here for in this case. And again, there's another link to learn more about it from the Pinecone site. So some other aspects of the vector databases that are definitely useful is that, as I mentioned, it allows for long-term storage and retrieval of your data and your embeddings. And then, again, that allows also for the long-term memory for being able to have those conversational type interactions. And then there's also data management. So as I mentioned before, in the absence of a vector database, you'd have to completely retrain your model with new data. But with the vector DB, you can manage data, adding new data, updating existing data, removing data. So, all your basic CRUD operations that you would expect from a database. It also includes metadata and being able to filter. Let's see, and then backups. You can make backups of your database for disaster recovery and that sort of thing. Also, you have integration with other tools. So ETL for being able to manage, and update that data on a regular basis, as well as dashboards and various plugins that have been created. And finally, just being able to manage access to your data, just like with other, relational databases or tabular databases, the security can be managed within the database. Some use cases. I've mentioned the long-term memory a couple times now, but also semantic searches. So as opposed to, I guess more historically, when you would do searches, oftentimes you'd have, it'd be a keyword search. So keywords would be defined in the database. So based on, the word that you're entering in your search or variations of that word would then serve up results based on that. But with the vector databases, it allows for semantic searching so that the application is able to infer the context and intent of your query. So an example here, highlighting the word bank. It has two very different meanings, and it can be inferred by the sentence. So, Sam going to a bank to withdraw some cash versus Jill pulling her kayak up onto the bank of a river. Another example potentially of semantic inference would be, based on where you are performing a search. So if you're looking for, doing a search on football players, for instance, your results would be very different if you're searching in the United States versus, say, somewhere in Europe. So semantic searches definitely provided a lot of additional power in that regard. And then similarity searches, show me, other shoes that are like these Air Jordans that I'm looking at. Recommendation engines. Of course, I'm sure everyone has seen the recommendations from Netflix. You may also like this show or movie. And then also sound searches. It's a little difficult to be able to put that into, a text field, but just an example here would be, when a song's playing on the radio and you ask Google to tell you what that song is.
Yeah, Tyler, I
Yeah.
want to say something about what you just said. That
Okay.
when you creating a vector from data, as you just mentioned, may be a sound, or it may be an image, or it may be text, or it may be whatever. And
Right.
maybe for good classification of images, I don't know, like to find groupings, it's interesting question how big should be the vector. Because Boris in earlier seminars, he showed how vector can be actually very small and still get pretty good search results. Whereas if you look at something like a Stable Diffusion, they use huge vectors internally, right? Like tens of thousands of numbers, literally. But of course, they manage to generate very good images with photorealistic high resolution output. But when you're working with large language model, which internally may have very high resolution, but for your own like search and classification purposes, the resolution of the vector doesn't have to be tens of thousands. It may be 500, and it will be probably good enough. So they don't have to be the same. And it's also interesting that you can create embedding for image and for search for text and create basically the same vector, and then use it to whatever like goal you have. Maybe to
Right.
find similar images, maybe to find similar text descriptions. So it's kind of interesting. Yeah.
Yeah, yeah, definitely. So up to this point, I've been talking about just conceptually the vector databases, but here's just a listing of some of the more common vector databases that are available. So some of the most popular, you'll see Pinecone here as the first one listed. Like I've pointed out several of the links that I've had from Pinecone. They have really a wealth of information on their site and a lot of really good information explaining a lot of these concepts at a high level. So the product itself, you'll see, is not open source. It won't necessarily be your go-to vector database, but the content that they have on their site is not necessarily specific to Pinecone. It's a lot of just really good general purpose information. And then some other really popular vector databases are the ones listed here. You can see most of these are actually open source. And then there are also a lot of other different vector databases out there available, some that are a little lesser known. One I do want to point out here is PG Vector. So this is actually an extension for Postgres to be able to leverage a well-known open source database and be able to use it for, as a vector database.
And as we discussed earlier today, we actually should have included SQL Server because apparently it also has support to vectors, which I didn't know until today.
True, yeah.
About Microsoft SQL Server. So both standalone SQL Server and on Azure cloud.
Okay, yeah. Let's see, this page just has a lot of links to the main pages for a lot of these different vector databases, as well as links to code showing you how to integrate the different vector databases into your application. So one thing I did mention earlier as well is indexing for your vectors. That really the indexing is critical to be able to get fast search results. And there are a lot of different ways in which the vectors can be indexed. So you can see here a list of several of the common indexing techniques. So locality sensitive hashing, product quantization. One that's used a lot, you can see here in a lot of the major vector databases, they all use they don't all, a lot of them use the hierarchical grid index. And many of them in combination with some of the other indexing techniques here. I do have a little bit of information here talking about specifically vector databases on Azure. So this first link here talks a little bit about using Azure SQL Database. This one, from when I was reading it, looked like it seems all right for doing similarity searches, but it seems to store each dimension of a vector in its own record. So it's a little different approach to managing that. Yeah, I'll talk a little bit more here in the next slide about SQL Server. And then also there's a service, the Azure Cognitive Search, that you can also use in Azure, similar to a vector database. Let's see, and one of the things, like I'd mentioned earlier, about using vector databases is the ability to, define your own data and be able to query your own data rather than necessarily having to pull strictly just from the language model.
Just can we just chime in? I talked to them, Azure people, so they say that it is a vector database. The prior vector database, they wouldn't tell me like what it is, but they say it is a vector. And the cognitive search are different options. One of them is semantic search, one of them is vector search, and the hybrid search. But vector search, they claim is their own vector database. That's all they would say. They wouldn't say like what it is.
Oh, okay.
Yeah. Actually talked to one of the reps.
Oh, okay. Interesting. Yeah, I haven't had a chance really to dive too much into that yet. So
it's hard to dive. I mean, I had to talk to somebody because you go through the pages and it's just like trying to put together some kind of a story. It's not easy.
right.
Yeah.
Yeah, they don't seem to.
Cognitive search. They have multiple. They have the semantic search, full text search. Still, they still have that on the web page. So we can use full text search and hybrid search. Hybrid search is a combination of vector and full text and possibly semantic search. And
okay.
yeah, I don't want to get distracted from. I just want to just kind of clarify that what they claim that this is real vector database, not some kind of something like it is a vector database, but that's all they would say. It's not of the existing database, not Pinecone, it's not Chroma. It's just their own database. That's how they say.
Oh, okay.
Yeah.
Interesting. Yeah, thanks for sharing that.
Sure.
Hopefully they'll publicize that a little bit more, particularly with the way interest in vector databases has really been exploding. So yeah, I would like to learn more about the Azure offerings, particularly as I mentioned, I work a lot with Azure, so I'd be curious to see how that's been developed on the Microsoft side.
Yeah, ask him. I forgot. I asked him what indexing they use. He answered, but I forgot what it was. I think it's the one that you had like in the HNCSW, but I'm not sure. Don't quote him in it.
Okay.
But yeah. Anyway, okay. No, thank you.
All right. Yeah, thanks. Let's see, and then let's so just to continue to talk a little bit more about SQL Server. Natively SQL Server doesn't have like array data types or vector database or vector data types. However, they have for some time had geometry and geography data types, which effectively are vectors because they are representations of spatial data. And so then there are functions within SQL Server that allow you to calculate the distance between these two different vectors. So there's some links here talking about how those data types can be used to leverage some of the functionality of SQL Server as a vector database. Let's see. And then jumping back to a little bit now, talking about some of the open source vector databases. Just have some information here about, in particular, some of the bigger players in the space are Milvus and Vespa, and some links here with information about those. And then also, as I mentioned, there's the PG Vector and PG Embedding extensions for Postgres that you can use. And just a little bit of interesting history here about Postgres database, how a precursor of that database began as the Ingress database developed at Berkeley. And then one of the leads on that project, later on, he wanted to continue developing it and adding some more modern database features, modern at the time. And so he took a lot of the principles that were used for Ingress and developed this post-Ingress database and called it Postgres. And then you can see that became open sourced, in the 90s, and then they added full support for standard SQL, and it became Postgres SQL.
Yeah, I want to add something.
Yes.
First of all, IngressDB started 50 years ago. So 73, yeah, 2023. So it's was around for long time. Second, that originally it was not tabular-based data. It was object-oriented. It had inheritance, and it still has. And that's why in PostgreSQL you could have vectors, and you can define your own operations. So it's like object-based database. And also about the above about PG vector and PG embedding. So these are two extensions, and yeah, well, you'll talk about them, right, on the next slide. Yeah.
Yes. Yeah, I'll have a little bit more about those. Let's see. So before I get too much into that, just a little bit of an aside here talking about LaneChain. I know we've had some discussions about LaneChain in past couple weeks in this seminar as well. But yeah, it's a framework for being able to interact with large language models and vector databases. Includes a lot of libraries to be able to connect to the different services and technologies. Developed by Harrison Chase and released last year, so it's still relatively new. But yeah, several links here about that and getting started with LaneChain. And then just a real high-level overview, the way LaneChain would work to integrate a vector database and a large language model in your application. So the first step you would do is you'd have to do your embeddings. So you've got your document, whatever your data might be. So it doesn't necessarily have to be like a text document, but whatever kind of complex data you might have. You break it up into chunks, and then those get embedded and stored in your vector store. And then using LaneChain, then you can integrate these pieces along with the large language model to be able to run your queries and pull those results from your vector database and get your answers or even take actions based on those results. So within LaneChain, out on GitHub, you can see there are a lot of libraries available for connecting to a lot of the different vector databases that are out there available. So again, Milvus is there. Let's see, you have the PG vector, Pinecone. So a lot of these are available. So here's an example of just using some code. This is available out on GitHub. But yeah, just importing the LaneChain libraries to be able to integrate with Milvus, so that one of the open source vector databases. So just to show how with Python code, it's relatively easy to get started and get going with just a few lines of code to be able to start working with your own vector database. Likewise, here's some code showing just how it can be used with Postgres. So including some of the Postgres libraries and creating your own table here with your vector embedding and being able to run some queries against that.
Yeah, can I say a couple of words about this? Because the
Yes.
first create table is just regular SQL, but then connection execute, whatever. This is actually from Python. It's a piece of maybe should have like used different color. And what you can do, you can combine regular tabular SQL with similarity search. So they're part of the same SQL. And you have two extensions, PG vector and PG embeddings, and they provide different functions. and you can have them both, and you can use them both in the same select statement in the same query. So they're just functions which allow you to compare data to find similarity. So this is really convenient because you have both a regular SQL database and similarity search together, and it's all open source and free. Yeah.
Yeah, definitely. Yeah, thanks for adding that, Lev. Let's see. So, yep, that's the Postgres integration there, and then just finishing up. Dimitri Khan, he's done a lot of instruction on vector databases and has a lot of content online. So I just have some links here to be able to reference some of his materials that he has relating to vector databases.
Did you see anything more current? I came across the 2021 comparison. First, I got excited, and then like, wait a second, this is 2 years ago. With this changes, it may be so relevant. You haven't seen any more current comparisons, right?
I have not. No.
Okay.
I know there's kind of a lot of information out there to sift through. So yeah, I haven't.
It was a good comparison. Like you look at those databases, but like you think, wait a second, that was pre GPT, right? It was pre all this
right
development. And,
actually, ChatGPT knows about Milvus and Pinecone, whatever.
He should, right?
Yeah, they were around for some time.
They pre-existed.
Yeah.
So anyway, yeah, that's my last slide. So thanks
Thank
everyone.
Tyler, I think it was very good, and
thank you.
Yeah, we're also good on time. It's less than 40 minutes. Guys, who have questions? Please ask questions. No questions?
Oh, I had a lot of questions. Tyler answered all my questions.
All right. Okay, then it's good. And then next lectures we'll talk more about large language models and about using LaneChain and go into more like practical examples. Thank you, Tyler. Thank you very much. Very much. Good.
Yeah, you're welcome. Thanks, everyone.
And as you go, please keep in touch. I'm really curious to know performance metrics, well, like SQL Server versus cognitive search versus Postgres versus Pinecone. Like, but we'll find it out in the next several months, I'm sure. Okay.
Right.
Bye, everybody.
Okay, bye.
Bye.